In this video, we're going to learn about something called the Moivres Theorem, and it's about complex numbers, which is something we haven't dealt with very much in this class at all in the past. And to me, it's kind of a funny topic because in your algebra classes, in your trig classes, maybe pre-calculus, you see a little bit of complex numbers, solving a quadratic equation, and sometimes you have a square root of a negative, so you put an I there, but you don't do a whole lot with it. And then you go into calculus and you pretty much pretend that complex numbers don't exist, that the imaginary numbers aren't actually there, and then you don't ever use them. And then when you finish your calculus sequence, maybe 2 years later, then suddenly you're going to start seeing it in later classes and they expect you to remember it. It's a really, in my opinion, a really weird scenario, but this is how it is. And in this section, what we're going to say, well, if we take a complex number, let's just say 3 plus 2i, we can think of it as a point in the xy plane where the 3 is how far you go right or left, and the 2 is how much you go up here. And so we can identify this point as 3 plus 2i. Now, once we've decided that we can do that, that we can represent a complex number as a point here with x and y, well, then we can go ahead and turn it into polar coordinates that we saw in our previous video. And we can go ahead and get our r and our theta, and we can write it this way. And mathematically, right, x is our cosine, y is our sine. So if we say x and I, y there, we get that, which we can factor out the r here. And there's a notation that's not super popular, but it's definitely out there, is instead of writing cosine theta plus I sine theta, they shortened it CIS, so r times cis of theta. It's just another way of writing that down. There's even another way that I don't really want to get into too much right now, but it's called like the exponential form here. You can write it as RE to the I theta, which again is not what we need today at all, but it's something that you may see if you look around things. And it does actually help you when trying to understand multiplying and dividing, because it turns out that if you want to multiply or divide complex numbers and you've written them in polar form, what you have to do is you just multiply or divide the radiuses, and then when you have your angles in your polar form, if you're multiplying, you're going to add those angles, and if you're dividing, you're going to subtract those angles. So I don't know if you guys have done this before, but you may or may not have seen a problem like this before where they wanted you to divide these two complex numbers. And what you had to do in that case is you would multiply top and bottom by the conjugate, and you do a whole bunch of foiling out, then you'd simplify things, and you get a big mess, and eventually you get to the right answer. This is just telling you that if you have them written in their polar format, let's say we had, 10 CIS 50 degrees divided by 2 CIS 20 degrees. I do 10 divided by 2 is 5. And for my angles, 50 minus 20 is 30. And so this would be my answer. So it makes multiplying and dividing complex numbers a lot easier. And there are applications where you're going to do a lot of that. For example, definitely in engineering electric circuits, you have to deal with things like this quite a bit. And so this just shortens that down if you have it in polar coordinates. Now, the specific Demarvorous theorem here is just saying that if you have a complex number in polar form and you want to raise it to a power, it's basically following the same rules. You just raise the radius to the power, and then you multiply the angle by that power. And what we can then do is we can use that to find roots, square roots, cube roots, and so on of a given number using this formula here, where it's again basically saying is, since we're taking the root rather than the power, although a root is a power, we're going to be dividing the angle by n rather than multiplying by n here. So in this example, I say find all cube roots of 8. So whenever you're trying to find any roots, the first thing you want to do is you want to rewrite this number in polar form. Now you might say, wait a second, 8 is not even a complex number. There's no I part, but there is. You can just think of it as a 0i. And so if we do it that way, then we look up here on our xy axis. If I go 8 and 0 in the y direction, well, my radius, my distance from the center, that's a distance of 8. And then I need to know what my angle is going to be. My angle is going to be, well, if I'm going directly right, that's 0 degrees. So based on that, I'm going to take the cube root of the r number here and get 2. And that means my 3 cube roots of 8. The first one is going to be 2 times CIS of the same angle divided by n. I'm doing cube roots here. Then I'm going to do the same thing where I take that angle, divide by 3, but now I'm going to add on a third of 1 full circle. And then lastly, I will add on another third of 1 full circle, which means my 3 cube roots are going to be 2 CIS 0, 2 CIS 120 degrees, and 2 CIS 240 degrees. And you can convert those into, a plus bi if you want to, or you can leave it in the polar form. But this allows you to find the roots of all the numbers you have. And the reason why this is important is if you think about solving the equation x cubed equal to 8, well, in the past you probably just took cube root of both sides and you got x equal to 2, and then you'd stop. But there's a problem here. We learned the fundamental theorem of algebra that says if you have an x cubed, you're supposed to have 3 answers. And yet we only have x equal to 2 there. And so there really should be 3 answers. And finally now we see the other 2 answers here. They're going to involve I. That's something we can't really avoid. But this shows you that we can get all the solutions to the equation now doing something like this.